Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUI campus. Okay, let's start with lecture contents first. In this video, we will discuss LTI systems and what is discrete convolution and what is continuous convolution. First of all, we will discuss linear time invariant systems. And to understand what is linear time invariant system, we must know what is linear system and then what is time invariant system. So the combination of linear system and time invariant system is called linear time invariant system. So first discuss linear systems. So when does the system will be linear? It means that the system will be linear when an input to a given system is scaled by a value. The output of the system is scaled by the same amount. For example, if you have a system L and you have an input X and output is Y. So if you scale the input by X, for example, scaling by alpha, so in output you should get the same scaling factor with the output alpha Y. It means that it's a linear and it should obey the superposition property as well. So there are two properties. If the system obeys that property, then the system is called a linear system. First one is obey the scaling property as I discussed here, and it should obey the superposition property as well. So what is superposition principle? The superposition principle is that if you have an input x1 to a system and you get the system or output y1, and similarly if you have a input to the system x2 and get this output y2, then these are two independent inputs, x1 to the same system L, and the x2 to the same system L, but these two are independent systems. So in result you get y1 and y2 respectively. Whereas if we just add these two inputs x1 and x2 and passes this to the system L, then in result you will also get the output, which is the summation of the two outputs y1 plus y2. So this is a superposition principle. So if any system which obey linear scaling property and the superposition property, then this system is called a linear system. Now discuss what is time invariant system. A time invariant system has a property that a certain input will always give the same output without regard to when the input was applied to the system. What does it mean that? It means that if you apply a system, for example, you have a system, time invariant system Ti here, and you want to give an input xt, so in result you get the output yt, right? What will happen if you apply the input xt minus t naught, the same input at the delayed time? The time delay is t naught, right? If you apply the same input but at the delayed time with some delay, right, to the time invariant system, in output you will also get the same output but at the delay time. So output is not changed, only the time is changed, like the reference point is changed. So it means that if you when the system you give the input to a system and it doesn't changes whether you applied at any time, it means that it's a time invariant system. So now let's discuss combination of linear system and time invariant system, which is called linear time invariant or LTI system. So certain systems are both linear and time invariant, so are thus referred to as linear time invariant system. Special importance for their mathematical tractability. It means that why these systems are important, because they are easily to analyze, and there are a number of other advantages of LTI systems. That is why we focus usually on linear time invariant system. Most signal processing applications involve LTI system, right? And LTI system can be completely characterized by their impulse response. So it can be completely described. It means that described by their impulse response. Let's check the linear time invariant system. So this is your LTI system and input xt, yt. and there are two properties. One is scaling and the other is superposition as well. So here uh, they are linear if you are applying the scaling factor, right? This is a linear property, and the other one is the time invariant, like you are multiplying by some, you are doing some scaling and also delaying. So this is for linear and this is for time invariant. Well, let's see what happens when it passes to the linear time invariant system. Then output is same scaled version and the at the delay time. So this is called a linear time invariant system. Now let's discuss the convolution first. So before going to the discrete and continuous, there can be two types: discrete for discrete signal and continuous for continuous signal. But the important thing is what is convolution. Uh, in a mathematical operator, it's kind of a operation, right? Like our addition, subtraction. This is another operation which we called a convolution. So this is kind of operation like we did subtraction, addition, and multiplication, so on. Similarly, there is one other operator which we call convolution operator, right? Which computes the point-wise overlap between two functions. For example, you have a function this one, right? This one, and another function is this one. Now you want to calculate the overlap between them, but point-wise. Point means like at each small portion, like this portion, you will evaluate portion by portion. This is called the pointwise. So you want to find the overlap between these two signals. So to find the overlap between these two signals, you will use the mathematical operator, which is called a convolution. Uh, right? The input signal is decomposed into simple additive components. Each of these components is passed through a linear system, and the resulting output components are synthesized. So first we will decompose the input signal into simple additive components like small components, and then in the resulting output is add to form the complete output of a system. So when an impulse decomposition is used, the procedure can be described by a mathematical operation called convolution. So this is convolution. When this convolution is used in discrete signals, then it is called discrete convolution, and when it is used in continuous case, then it is called a continuous convolution. So let's discuss more in detail what is discrete convolution. In discrete convolution, first of all, we will consider the linear time invariant systems because these are good models for many real-time systems, real-life systems, and they have properties that have led to very powerful and effective theory for analyzing their behavior. So LTI has number of benefits or advantages due to which we will consider the LTI system for analyzing the system. So in the following, we want to study the LTI system through its characteristics function called the impulse response. So any system, and the LTI system especially, can be described by an impulse function, impulse response. What is impulse response? For example, you are at the input, this is input of a xn, this is your LTI system. When you give the input, which is delta n, which is impulse, right? Delta n is impulse. When you give the input here to the LTI system, the response you got from that system, like the output you got yn, it is hn, right? So this response is called impulse response. When you give at the input the impulse, then the response that you got from giving this input is called the impulse response. So let us consider a discrete time signal xn, as I already mentioned. Denote hn the impulse response of a LTI system s, right? This is the LTI system denoted by s. The impulse response, as it is named, is the response of a system to a unit impulse input. You applied unit impulse, right, which is only 1 when n is 0, and Otherwise it's 0. Like for other n, it is always 0. So when you apply impulse here, you get the response. So it is called the impulse response, right? So to begin with the convolution, we will start with the representation of discrete time signals and linear combinations of delayed impulses. What does it mean? I once I discussed with you previously in the class that we can use the impulse, right? This impulse delta n to which is 1 at n equals to 0, right? N equals to 0, it is 1 only, right? Once we discuss its shifting property, that when it is shifted and you can get and shifted version when multiplied to anything, for example you multiply xn, right, by delta n, right, in result you will get x0, right, because it is only 1 at 0, right, you will get the 0 sample. Similarly, if you multiply by n minus 1, so it means that n becomes 1, so you will get the output at x1, so on. Let's discuss first. So what we are discussing here, that we can we can write the x of n sample in terms of, this is your given input, right? We can write this in terms of impulse function, impulse responses, right? Like in terms of delta n, we can write this one in this way. Let's see how we can write. We have shown that previously x and delta n minus n naught is equal to x n naught delta n minus n naught. We already discussed in the class. For example, if n naught is 1, right? So you will get what? You will get x1 as the output, right? So n minus n naught delta n minus n, right? Using this fact, we can get the following equation. So for example, you have x and delta n. So n equals to 0. So x0. So delta 0 1. So x0 in the output you will get x0, right? Or you can say x0 into delta n. Similarly, x n delta n minus 1, here n naught is minus 1. So put you in result you will get the x1 sample, and the position of the sample is at delta n minus 1. So similarly, x and delta n minus 2, you can get x2 delta n minus 2 when n naught is where n naught is equal to. If you generalize this one, you can get xn summation k is equal to minus infinity to infinity delta n minus k. And whereas this you can write as k is equal to minus infinity xk delta n minus k. We can generally write this one in this way, right? So somehow on the left hand side, this one is equal to xn. You know that because if you multiply this one with any factor like delta, because delta n is 1 for k different values of k, but only the shifted one. In this way you only get the reference point. For example, n minus 1, you will get xn minus at the position minus 1, and x2 at the position x2, so on. Because delta n k minus k equals to 1 for all n, right, as you know. Because this is delta function which is 1, when n changes it will only shift to the different places, but the result will always be 1. So the sum on the right hand side is equal to k is equal to minus infinity xk delta n minus k. Therefore, equating the left and right hand side, we can get xn in terms of xk delta n minus k. So in this way, we can write the given signal in terms of impulses. So in other words, for any signal xn, we can always express it as a sum of impulses. So in this is another way of writing the same signal in terms of impulse, right? This is nothing else, uh, just we divide the given signal xn into in terms of impulse, right? Because xk n minus k, so we will get in the end And at k is equal to minus infinity, we will get the minus infinity x of minus infinity. For k is equal to 10, we will get x of 10. So it's same, but in terms, we write that in terms of impulse function, impulses. So next, we suppose that the impulse response of a LTI system is Hn. We already discussed, and we are supposing here that if the impulse response of a system is Hn, so we want to determine the output Yn. Now we want to determine what is Yn, means the output. To do so, first we express the Xn as the sum of impulses, as we already proved on the previous slide. So using that, we represent Xn in terms of Xk delta n minus k. If you are still not clear with this, then to understand this, see my previous lecture where I explained in more detail what is Xk delta n minus mk, how we can write this in terms of impulse. So for each impulse, when we input to the system, we can determine its impulse response, because there are minus infinity to infinity impulses, right? Because k varies from minus infinity to infinity. So for each impulse, we will input to determine impulse response, we will input to the system, and we will get Hn minus k in general. So consequently, we have Xn is equal to Xk delta n minus k. Previously, we have this one, right? But now, because we are passing through a LTI system, so in result we will get minus infinity to infinity xk, and in terms of delta we will get h, because we are passing through a system. So we will get xkhn minus k, which is equal to the output yn, right? Hence this is the equation to find the this is equation which is known as the convolution equation. So xk hn minus k is the convolution equation in terms of discrete signals, right? So for to find the discrete time convolution of a signal, you use this one. This is your input, and this is your impulse response. So multiply these two, or do this procedure, and you will get the final output of the system. And given a signal xn, the impulse response of LTI system is Hn. So the convolution between Hn and Xn is defined as this one, Yn, as I already discussed in the previous slide. So we denote the convolution as Yn is equal to Xn into, this is convolution operator, right? Steric Hn. So Xn is steric Hn. This is convolution. So we can write this equation in this way as well. So it means that these both are equivalent, right? So you must remember that convolution is true only when the system is LTI. It means that it's not a time varying system. If the system is time varying, then Yn is calculated in this way: xk, and here you will have a h of k. There is an index k here as well, and n minus k. Hn is different at every time instant k. It means that Hn is different for different time instant k. So the following standard properties can be proved easily. It means that convolution obeys these three properties, and we can prove as well, but we are omitting that one because of not necessary to prove it. So it obeys the commutative property, like xn convolution hn is equal to hn convolution xn. It means that you can interchange both of them. It will not you will get the same result. Either you do write hn first and xn later, right? And it also obeys the associative properties. What is associated, like xn into h1 h2 are equals to xn into h1, and you get the convolution out of this one as well. So a distributive xn into h1 plus h2n equals to xn, sorry, it's n not t. So xn into h1n plus xn into h2n. So these three properties, the convolution operators also obeys these three properties as well. For continuous convolution, okay, in developing convolution for continuous time, the procedure is same as in the discrete time, although in the continuous time case, the signal is represented as a linear combination of narrow rectangles. So in general, you can find the convolution output convolution as this one. This is your input and this is your impulse response, right? So minus infinity to infinity, they have an integral instead of summation, because in discrete there was a summation, whereas in continuous there is integral theta. Approximation of a continuous time signal as a linear combination of weighted, delayed and rectangular pulses. Let's see how can we write the input signal this x of t in terms of a linear combination of weighted, delayed and rectangular pulses. Similarly, as we write the discrete signal in terms of impulse, right? We can write here in terms of a weighted, delayed and rectangular pulses. Let's see here. Continuous signal representation in terms of a linear combination of narrow rectangles. For example, this is your signal x of t, right? And you want to, this is your continuous signal, right? Going here to here, right? This is in this way, right? Now you can break this signal into small rectangular pulses, right? This one, this one, this one. So these all are rectangles, right? Small rectangles, and they have a width of delta, because minus delta to 0, 0 to delta, 2 delta, 3 delta, so on. So the spacing between each rectangle pulse is delta, right? So we can write xt in terms of delta function, small impulse, narrow rectangle function in this way. X0, this is your, for example, the zeroth sample which lies at 0 position, and impulse into delta. Impulse is 1, but the width, as the width is delta, so we are multiplying this width as well. So delta t into delta plus x delta, it means that here is this point x delta, we are getting delta t minus delta. So this is referring to this is the impulse at t minus delta. It means that will only get the output at x delta. The reason to multiply any impulse, you will get the value only at that position, because impulse is 0 at other position, right? And into delta means we are getting the area of this one, like the delta, this is width of this one, and plus x minus delta, x t plus delta into delta, so on. So xt equal to summation k minus infinity to plus infinity x k delta. In general, we are writing now delta t minus k delta into delta. Xt is equal to limit delta approaches to 0, as we consider that delta is very small, then x k delta delta t minus k delta into delta. So if we write, because this is area, so we take the integral. So minus infinity to infinity x star t minus star delta d star, right? So we can write xt in terms of pulses in case of a discrete time, sorry, in case of a continuous time signal in this way. So x star delta t minus star, and this is the pictorial view of each position, like this one x0, this one x01, right? And 0 to delta, so x0 delta and into delta, so delta is due to this width, right? So on for t minus delta, where the difference is delta minus 2 delta is always delta, so that way we kept delta constant here. Thank you for listening, and for question answer session there will be some reserved slot, so exact time will be communicated later on. Thank you.